In this video, we're going to look at limits involving the remaining indeterminate forms. So the first one is anything that is 0 times infinity. So if you can, you want to try to write it as 0 over 0 or infinity over infinity so that you can use L'Hopital's rule. So as x approaches infinity in this problem, x is going to approach infinity, but e to the negative x, remember, is 1 over e to the x. And as x approaches infinity, this whole fraction approaches 0. So this is an infinity times 0 or 0 times infinity. So what we want to do then is we want to try to rewrite this in one of the indeterminate forms we know. So I'm going to actually make the change where we have, instead of e to the negative x, 1 over e to the x. So this is now the limit as x approaches infinity of x over e to the x. And this is something that would approach infinity over infinity. And we know that that is a situation where we can use L'Hopital's rule. So I'm going to take the derivative here, which is 1, and the derivative here, which is e to the x. This is now a number over something approaching infinity, so we get 0. Notice again that I don't drop the limit notation until I can actually evaluate the limit. And when I go from here to here, I'm not using L'Hopital's rule again. I'm only using it from this step to this step. In this case, we have the indeterminate form 1 to the infinity power. So this is an example of that. We've got the limit as x approaches 0 from the right of 1 plus x raised to the 1 over x power. So this whole fraction here, as x approaches 0 from the right, is going to approach 1, and this exponent is going to approach infinity. And anytime you're dealing with a problem and you have variables in your exponents, you may need to use some logarithms. So the way we approach this indeterminate form is we want to start by setting the variable y equal to our limit. So I'm going to let y equal the limit as x approaches 0 from the right of 1 plus x to the 1 over x power. And then what I'm going to do is I'm going to take the natural log of both sides. So I'm going to take the natural log of y is equal to the natural log of the limit as x approaches 0 from the right of 1 plus x to the 1 over x power. So one rule to remember that is handy in this is that if you have the natural log of the limit as xc of f of x, that is the same thing as the limit as x approaches c of the natural log of f of x. So the order of the natural log and the limit are exchangeable in this case. So that means I can now write the natural log of y is equal to the limit as x approaches 0 from the right of the natural log of 1 plus x to the 1 over x power. So why do I want to do that? Well, that allows me to take this 1 over x and pop it out front of my natural log. So I now have the natural log of y equals the limit as x approaches 0 from the right of 1 over x times the natural log of 1 plus x, or natural log of 1 plus x over x. We're talking about what happens as x approaches 0 from the right. So as x approaches 0 from the right, 1 plus x is going to approach 1. So this natural log is going to approach 0. As x approaches 0, this x is going to approach 0. So now we can use L'Hopital's rule. So we get the natural log of y equals the limit as x approaches 0 from the right of the derivative of this, which is going to be 1 over 1 plus x, divided by the derivative of this, which is going to be 1. So now we have the natural log of y equals the limit as x approaches 0 from the right of 1 over 1 plus x. And this is something we can actually just directly substitute into. The natural log of y equals 1 over 1 plus 0, or the natural log of y equals 1. So now I can raise e to both sides. E to the natural log of y is just y, and e to the first power is e. So I get y equals e, And if you remember at the beginning of the problem, y was equal to the limit we wanted. So the limit now as x approaches 0 from the right of 1 plus x to the 1 over x power is equal to e. That's the answer that we want. This problem is going to work very similarly. We have the limit as x approaches 0 from the right of sine of x to the x power. Sine of 0 is 0. Obviously x is approaching 0 as well. So we're going to let this be equal to y. And I'm going to take the natural log of both sides. So we'll have the natural log of the limit as x approaches 0 from the right, x to the x power. And then just like before, I'm going to swap the limit and the natural log. I'm going to use the power rule to bring this x out front. And now I have the limit as x approaches 0 from the right of x natural log of sine of x. So in this case, this is something here that is approaching 0, and this is something that is approaching, if you're taking the natural log of sine of x as x approaches 0 from the right, this is actually going to approach negative infinity. So one thing you have to keep in mind, there's kind of a nested thing here, but the graph of natural log of x looks like this, right? This is natural log of x. And as x approaches 0, sine of x is approaching 0. So the natural log of sine of x is approaching negative infinity. Okay, so what we need is an infinity over infinity type rule, because unless you want to deal with cosecants, which I don't think you do, you're going to need to leave this infinity here. So what I'm going to do then is I'm going to write this as the limit as x approaches 0 from the right of the natural log of sine of x divided by 1 over x. Now you can see that if you did keep change flip, that would just bring the x right up front and you'd end up with what you had there. So the reason why this works is because obviously we know that this one goes to negative infinity. We've established that with the graph. This one though, as x approaches 0, 1 over x is going to approach infinity. So now we can use L'Hopital's rule to get the next version of the limit. The natural log of sine of x, the derivative of that would be cosine of x over sine of x. And the derivative of 1 over x is negative 1 over x squared. So that's what L'Hopital's rule gives us. Okay, so now from here, I'm going to do a little bit of tricky algebra and a little bit of trig. I know that cosine of x over sine of x is cotangent of x, but instead of writing it as cotangent of x, I'm going to actually write it as 1 over tangent of x. So I will have tangent of x in the denominator. I'm going to have a negative out front, and then I'm going to keep change flip to bring this 1 over x squared up to the top, which will be x squared. So I have negative x squared over tangent of x. So now, as x approaches 0, this thing approaches 0, and this thing approaches 0. So I get to use L'Hopital's rule again. I'll have the limit as x approaches 0 from the right of negative 2x over secant squared of x. And as x approaches 0, this approaches 0, but the secant squared of x approaches 1. So we get that the natural log of y is equal to 0. And if we raise e to both sides, we get that y equals e to the 0, which is 1. So our whole limit is equal to 1. Now we're taking the limit as x approaches 2 from the right of 1 over x squared minus 4 minus the square root of x minus 1 over x squared minus 4. And you may notice with both of these, you have 2 from the right. So these are both evaluatable themselves, okay? But when we put them together, it's a little bit of a problem, because here we would have a fixed number over something approaching 0, And because we're coming from the right of 2, this would be a slightly positive number. So this is going to end up being infinity. Okay? And with this one, you're going to have approximately 1 divided by something that's really, really close to 0. So the question is, which infinity is larger? Does one overpower the other, and what's the difference between them? It's hard to say, right? So this isn't considered an indeterminate form, and there's a bunch of different ways that you can approach this. Typically, though, whenever we're dealing with an indeterminate form, we want to try to break it down to something that is either 0 over 0 or infinity over infinity. So what I'm going to do is observe with these two that I have a common denominator. So I'm going to write it as the limit as x approaches 2 from the right of 1 minus the square root of x minus 1 over x squared minus 4. So the reason why I'm doing this, if I were to plug the 2 in here, I would have 1 minus the square root of 1, so that would give me 0. And here I would have 4 minus 4, which would give me 0. So now I can use L'Hopital's rule and take the derivative of those. And I am aware that the numerator here is a little bit challenging to find the derivative of. The derivative with respect to x of 1 minus x minus 1 to the 1/2. I mean, it's not impossible, it's just a little challenging. It would give me 0 minus 1/2 times x minus 1 to the negative 1/2 times the derivative of the inside. So that's going to give you negative 1 over 2 square root of x minus 1. So that's what I'll have on top, negative 1 over 2 square root of x minus 1. And then on the bottom, I'm just going to have 2x. So we got to do a little bit of cleanup. We'll get the limit as x approaches 2 from the right of negative 1 over, let's see, we'll have negative 1 over 2 square root of x minus 1 times 2x in the bottom. So that'll be 4x square root of x minus 1. Now the nice thing about this is we can now plug this in because nowhere in this denominator are you going to get a 0. So this will be negative 1 over 4 times 2 times the square root of 2 minus 1, which gives me negative 1 over 8 times 1, or negative 1/8. So the limit as x approaches 2 from the right of this entire function is negative 1/8. This is a similar idea because you're taking the limit as x approaches 0 from the right. You've got 10 over x and 3 over x squared, and they're being subtracted. A number over 0 is going to go to infinity. A number over 0 is going to go to infinity. So I'm going to try to find a common denominator. I think that common denominator is going to be x squared. So I'll multiply this one by x over x, and I'll get 10x minus 3 over x squared. Now, in this case, if I plug in the 0, I get 10 times 0 minus 3. So this one is going to approach negative 3. This one is going to approach 0. So my limit here, a fixed number over 0, is going to approach either positive or negative infinity. So in this case, because I'm squaring it, the number's positive. I know that this one is going to be a negative number divided by a positive number, so this is going to end up being negative infinity. But what's really important about this example is that nowhere in this example did we apply L'Hopital's rule. You need to understand when you're using it and when you're not. You have to have either a 0 over 0 indeterminate form or an infinity over infinity indeterminate form. So we had one here, we had 0 over 0, so we used L'Hopital's rule. Here we used the idea that we had a fixed number over something that was approaching 0, so that is not L'Hopital's rule. So it is important to understand the difference between when you're using it and when you're not.